So I'm recording today, but I think I'm going to be doing more board work than talking to the slides on the computer or the notes on the computer. So we'll see how valuable the recording is. Um, Today is the background section of your report due. Technically, homework 2 is due today, but I haven't posted it, so probably hard to make you turn that in. I'll get that posted in a day or two. I've had some reports that were due recently that took up all of our time. If you talk to Omar, you'll you'll know he's probably said very bad things about my name. So anyway, those are basically in review at this point. So the workload eased off of it. Anyway, I'll get those posted. I'll give you basically a week notice for each homework. I don't think you should post homework and require that it be done the next day. Let's talk about background a little bit. Background sections due today. I've looked at a couple. The main issue that students have with sections like this in a report, background sections, is they don't put in enough detail. So the point of this from the reader's standpoint is I need to know what you're talking about. So you need to define all your terms. If there's something that you want to talk about, efficiency, don't just say the word efficiency because I don't know what that means. You've got to give me the mathematical formula that you're going to use to measure the efficiency of whatever you're measuring. If you're going to talk about throughput, I need to know what that means. Okay. So with yours, it's kind of odd, like time to convergence or something like that might be a metric, but you have to define what that actually means. What does convergence mean? Right. So that's the kind of thing that typically students don't go to that level of detail, typically. Now, again, from the reader's standpoint, what I'm saying is I need to know this stuff to understand what you're doing and judge for myself if it's valid or not. But more importantly, from your standpoint, what you're doing is you're making all of the hard design decisions as early on as possible. So the tendency, especially with software, is, oh, I'll figure it out when I'm coding. And that is a lie that we love to tell ourselves, and it is a lie. It won't work. You won't be able to figure it out. And if you do figure it out, you might figure out that half of what you did previously has to be rewritten. So everyone's nodding. Yeah, I've done that. I've done it too. So the benefit from your standpoint is it forces you to work through the hard problems now rather than being what normal human beings do and saying, oh, I'll figure it out later. So that's why I'm trying to insist that you get as much detail and definition in there as possible. Today and tomorrow, today's the discussion about statistics. Tomorrow is the discussion about statistics. I think today we'll get through all of the definitions, and then tomorrow we'll just work examples. But I want to do the same thing as I've been doing, which is lecture for a while, but then reserve some time to talk to you about your reports and give you some feedback. So we're talking about statistics. And the reason we're talking about statistics is you generally, in the real world, will have situations where events occur, and then the events can occur in different ways. And as a general rule, you can't come up with a formula and say, this is exactly how this event will occur. Now, there are situations where you can come up with formulas, and we use them in engineering all the time. So those people that are in the aerospace engineering program and the civil engineering program, they study things like cantilever beams or pinned beams, and they say, here's a beam, here's how it's supported on each end, here's what the load is, here's what the material is. And then we're going to calculate what the deflection of the beam at the center point is. And that's something that is not something that is amenable to like statistical effects. In the real world, there will be some variance and therefore statistics come into play. But basically what they've got is a closed system. They've got a closed problem, a solved system, and they're able to predict with good accuracy, engineering accuracy, what the actual effects will be. However, in the real world, especially in an agent-based world where decisions are being made, you're going to have variations in the output. And then the variations in the output start to become something that are much harder to describe. So if you're doing analysis of a structure under a certain load and you know what the structure components are, you can say with a great deal of certainty, here's the maximum stress, here's the point at which it'll fail, and I know that I'm correct within, plus or minus 10%, something like that. And that's good enough for the engineering world. But like I said, in many situations, especially where outcomes are variable over time, you can't say things like that. You have to resort to statistics. Now, I said that the engineers get away with this closed form solution, and that's true. They do. But even then, they're operating in a statistical world, and most of them don't realize it or don't pay that much attention to it. So for example, whenever they say, oh, we need to accept this kind of a load on a structure, therefore we have to use a specific metal with a specific heat treatment so that we can achieve a certain level of stress and strain that this structure can support. Then they go to a book called Mill Handbook 5 and they look up materials, and Mill Handbook 5 will tell you, hey, for a steel with 5% chromium and blah, 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 whatever, and this particular heat treat, this thing can withstand 150,000 PSI of pure tensile strain, tensile stress. All right, that's great. What that means is when you get that steel bar or that steel sheet from the manufacturer, that what they're saying is they're guaranteeing that it will withstand 150,000 PSI or whatever the number is. However, what it really means, it's actually framed again statistically, what it really means is this. They have 5% confidence and 10% confidence. And if they say, hey, the steel that you get, and I'm going to simplify this, the steel that you get will support 100 pounds. That's what we're going to give you. We're going to sell that to you. It'll support 100 pounds. Here's what that really means if you read all the fine print. What it really means is 90% of the steel that we send you will support 100 pounds. Some will support more, but 10% will support less. And then it gets worse than that. And if we sell you batches of these things over time, we're saying that only 95% of those batches will actually meet that requirement. So the requirement, when we say that in the engineering world, this material meets this threshold of being able to support a load, what we really mean is 90% of these will meet it 95% of the time. So notice there's a double layer there. That's a kind of a weird way to think about the world. And that's why, for the most part, once you get used to doing some kind of engineering, and I did this for several years in industry, you keep that in the back of your mind, but it doesn't come into your equations. You're just like, okay, here's what we do. And that's why you put in factors of safety and things like that to account for those kinds of variances. So here's my question. Somebody says to you, I'm going to sell you these iron bars, and these iron bars, each one can support 100 pounds. And by that, they really mean 90% of them will support the 100 bars 95% of the time. If it's a really high quality system, it might be 95% support at 95% of the time. But let's say 90% support at 95% of the time. And they sell you these iron bars, and it turns out half of them don't support 100 pounds. Half of them don't meet the criteria. Here's my question. Have they violated the contract? Okay, yeah, so they gave you 100 bars and 50 of them failed, right? That was one shipment, right? And you're right. They have not violated the contract. Why? because 95% of the time they have to meet that load, but 5% of the time they can fail. Now, what if they send you a second, you call them up, they send you a second batch, they also fail. Have they violated the contract? Not yet, right? Because 5% of the time they can fail. Now, what does that mean? Let's pretend that they made 1,000 batches. 5% of 1,000 is 50, right? That means 50 of those batches will not meet the requirement and they're still meeting their contractual obligation or their advertised stress and strain. You might have been unlucky and gotten 2 in a row from the bad 50, right? That's how statistics works. You can't just say with certainty, this is 100% certain that this event is happening or this event is a failure of the contract or whatever. You can only say, statistically speaking, it is unlikely. Now, granted, if you get a third batch and a fourth batch and a fifth batch and they're all starting and none of them work, it becomes statistically unlikely that they're actually meeting their contract. Again, think about it. With the 10,000 batches, if 50 of them are bad and 9,950 are good, what are the odds that you're going to keep getting shipments from the bad 50, right? Basically, every time they grab a batch, if it's truly random, you've got a 95% chance of getting a good one and a 5% chance of getting a bad one. And so the fact that you keep getting bad ones, it's not impossible, but it is also not statistically likely. And that's the way you frame these things. So again, when you frame the conclusions of your experiments in this class, it's virtually impossible for you to say, oh, we did this effect and this effect improved the throughput, right? It improved the behavior of the system by 10%, or it improved the behavior by 20%. What you have to say is something along the lines of, it improved the behavior of the system at 10% at 10% confidence or 5% confidence, whatever. You have to put that qualifier on there. Because for all we know, let's flip it around. Let's say that in your experiments, you run some baseline experiments and you get a set of results. Then you inject a change into the system, what you hope is, say, an improvement in the system. And then you get another set of results. And you run your test 10 times. And each time in the 10 times, things were better than in the baseline. Does that mean that your effect truly had an improvement, truly resulted in an improvement in the system? Or did you just get lucky? And that's the question, right? That's the question statistics is trying to answer. So it could be that there were 1,000 possible results that could come out. 10 of them are good. 990 of them are bad. And you got lucky and you found the 10 good ones. Possible. Possible. By the way, this is why I don't know about you guys. I went through MA241, MA242, MA243, DiffEQ. I breezed through those classes. It was so intuitively clear to me what was happening. And then I hit statistics and I was like, I have no clue what's being said here. So I'm trying to frame these things in a way that are very much layman terms, not just mathematician terms. But that's basically the question that you're always asking yourself. Is the effect that I saw, this change that I saw, is it real? Or is it just the luck of the draw? That's what these questions always come down to. And it could be, there's basically two forms to that question. One is, I've got two different populations, but I'm being told they're two different populations, but are they really the same? And the other form of that is, I have a single population, I inject some kind of change to it. So I've got basically a before and an after. And I want to know if the before and the after, are those changed? So for example, let's say in a class that we're teaching, we say, you know what? I heard of this great new teaching technique. It's called whatever. And so I'm going to try it. And so what I do is I take a semester's worth of students and I give them some kind of a exam, and we'll call that the baseline. And then I try my new teaching method. And then after the teaching method for the next set of students, next semester, I give them the exam, and then I look at the results. Now, how can I tell if my new teaching method, this intervention, actually made a difference? How could I tell? And I'm saying exam, but it could be that you look at all, I gave in the fall semester, I gave all these students 10 homeworks. And in the spring semester, I gave all these students 10 homeworks. And I'm going to compare the homework grades. I'm going to see if they did better on the homework based on this new teaching method that I'm trying out. And then I'm going to see, did the new teaching method actually have an effect? So what am I going to look for? What pitfalls are there? What problems could I have with finding this out? Yeah.
The sample size.
The sample size. So for one thing, let's say in a class like this, we have 6 people in the fall and 6 people in the spring. That's not a great sample size. What you would like is to get a class like COM 122 that's got like 1,000 students in the fall and 1,000 students in the spring. But now you've got a new problem, which is multiple instructors, right? So sample size is an issue, right? Maybe you're going to get 30 or 60 students if you're lucky fall, 30 or 60 students if you're lucky spring. That's one issue. Are there other issues?
They want to their homework.
Okay.
If they even do it, like the outlier.
Okay, yeah. So then outliers is a problem. Yeah. So if the work, what do you do with students that just don't do the assignment? Right? That's an issue of how do I score this stuff? We're going through this issue now because we're reporting to ABET for our accreditation, and we assess student work. And then some of our students didn't turn in any work at all. And we had a big discussion in the faculty meeting of, do we call that a failure? Or do we call that just don't even count that student because we don't know what their skill set is because we don't have any evidence either way. And so there was a good half-hour discussion about how do you count that. If they don't do the work, that's going to artificially drag the score down, right? The average score down, but it doesn't mean that student doesn't know the skill. It just means they didn't do the work. Yeah, well, okay, so let's talk about that. Would the effect be the same in both semesters? See, so if the fact that it's homework means that students are getting external help or something like that, where the scores are artificially inflated from their basic skill level, it might be the same in both semesters. If you use the same homework assignment in both semesters, you have to worry about, did anybody from the spring semester talk to people in the fall semester and get answers from them? Like used to happen, I assume still happens with fraternities and things. They keep files of this kind of stuff, right? So there may be, these are confounding variables, right? How about the fact that maybe in the fall, I've got some students, a set of students who quite frankly, just by the luck of the draw, there was a large population of students in there that quite frankly just weren't very good students. Like they dropped out at the end of the fall semester. And then in the spring, maybe I've got a set of students just by the luck of the draw who are more high performers. I've seen that happen. I mean, talk to any faculty member and they won't embarrass any specific student or anything like that, hopefully. But I have had semesters where just the student skill set, for whatever reason, in that one class in that one term, just didn't seem to be normal. And I've had others where they were like, as a group, a little bit lower in terms of skill level. And then I've had others where they're higher. After COVID, we were getting freshmen that were coming in that quite frankly had lost a year of high school. And so of course their skill level, and they felt a lot more, I guess some of you guys might be in that group, right? They felt they were expressing a lot more anxiety, quite frankly. And as an instructor, I had to help them manage that anxiety to the best that I was able to, which wasn't that much, but so these kinds of things can all be confounding the experiment. Then when you do get a difference, we say, okay, we tested all the students in the fall, we tested all the students in the spring, we got an average value in the fall, we got an average value in the spring, and the average value in the spring went up out of a score of 0 to 100, it went up half a point. It went from 82 to 82.5. So did the teaching intervention have an effect? Doesn't seem right. That seems like a really small number. What if it went from 82 to 83? What if it went from 82 to 97? At some point, intuitively, your gut's saying that seemed to have an effect. But where's the line? Where's the line? And that's, again, what statistics tries to answer. That's what that whole Z-test is about, is comparing two averages and trying to figure out, are these difference in averages blind luck? Or are these difference in averages because of some real effect that I need to take into account? So the issue here is it's always the same thing. I've got two populations that I'm comparing, and I'm trying to determine if they're the same or if they're different. Now, I'm framing that question either because I truly have two populations and I want to see if their behavior is the same, or I've got like a before and an after. My populations are some kind of before and after. And ideally, the before and after are actually the same in terms of human subjects, the same people. That's generally how that works. So again, in the example I had with the fall semester, spring semester, I'm going to have different people. And the fact that you have different people right there is an issue, unless you can get a really big sample. That's why if you look on political polling, they're always like, we polled 900 people. They generally poll at least 900, and they'll go sometimes up to a little over 1,000. And then they'll say, and we believe our rate of error is like 3.4%, plus or minus 3.4%. So if we say 60% of the people support X, what they're really saying is 60% plus or minus 3.4%. And they put that in. And how are they getting that? They're getting that from this, basically the way distributions behave, and the fact that they have a sample size of a certain size sample. We have issues in testing with humans. And the polling, they talk about this a little bit, but you can imagine, let's say we do the people over in the College of Arts and Sciences, human factors. They're going to do an experiment. And so they're going to say, okay, we want to figure out what the right color is for this particular indicator. So we're going to test a bunch of students. I don't know. And then they tried students, and they could do a bunch of students. Why are they doing a bunch of students? Because students are on campus, right? So they have access to students, and we'll pay you $5 or whatever. I don't know. Do they do this in College of Arts and Science? Do the human factors actually like pay you $10 or anything like that to take an experiment? Thanks. So you can go. Yeah. Okay. Okay. So yeah, but it's spendable on campus. It's campus money. Okay. So they're rewarding you though they're trying to entice you to come in and do the experiment. Have you done any? Have you any? No. Okay. So right off the bat, can you see an issue that they might be having with their experiment, regardless of what the experiment is?
Sample size.
Exactly, and that's called selection bias or sample bias. And there's two ways that there's bias occurring here. One is you're only testing things on college students, and if you try to apply that to the general population, that may or may not transfer well. And then even within that sample of college students, you're getting college students who are poor enough or hungry enough to want to work for food, basically, is what you're telling me, which I was always that person. I'm still that person. So
To get $5. And like.
yeah, so you're not even getting minimum wage. Yeah, yeah, yeah. And I suspect a lot of the students are human factors students. So again, you're even getting a smaller, more biased sample. All right. So how does that transfer to modeling and simulation with a computer? Because with a computer, are you going to get sample bias or not? How could you possibly get sample bias? Right. You are embedding your biases. You are embedding, and quite frankly, this could come out very subtly where where humans are very good at, we're good at convincing ourselves that we're not cheating or we're good at convincing ourselves that we're being objective when sometimes we're not. So if you already have a belief about how things will behave in your simulation and you encode that belief in, even that becomes a form of bias all by itself. If you say, hey, in my UAV world, if I implement this new policy, things are going to get better, you may actually encode things that make it better, whether or not the policy is good or not. You'll just say, hey, when the policy is in place, everybody moves faster or whatever. And you may not do it very blatantly. You may do it, quite frankly, at a subconscious or an unconscious level. Now, you may do it blatantly. If you are an unethical person or an unethical company, you may do it blatantly. And there's a famous case, I don't know, it's been maybe 10 years ago now with Volkswagen, with the emission standards. So the Volkswagen programmed their engines in such a way that when they were doing the testing for the emission standards, it behaved one way and gave great clean emissions. And then when they were operating in the real world on the highway, they were in a different mode and they were getting better performance, but they were also polluting far more than their testing had indicated. Now that was a deliberate, we are trying to evade the requirement that we have to have certain amount of clean emission, right? That was just a complete ethics breakdown, top to bottom, right? Management down to the programmers. I don't suspect that's going to happen in here. There's no value. For one thing, there's no value in it here. One of the good things about having an experiment is you can't fail, right? You have a hypothesis, and the hypothesis is either borne out by the experiment or it's not. Either way, your experiment was a success. If you're able to provide an answer, yes or no, with some kind of a confidence level, that was a successful experiment. And I mentioned earlier in the semester, people don't publish their failures. So if you say, here's my hypothesis, I think that this technique will improve the process, and then that technique did not improve the process, publish it anyway, or act as if you're going to publish it anyway. And the reason is you're going to save someone else a lot of time by, going down the same road. Yeah.
Sad about that is that academia values the failures a lot less. I was having a lot of problems with that.
Yeah.
Experiment like that last year too, and it ended up not working.
Right.
But I still tried to publish it because it was interesting.
Yeah, you should. Yeah, and it's exactly right. First of all, people are not as likely to publish, and secondly, yeah, it may be harder to get it accepted.
Yeah. For getting 2 rejections, I just redid it, and now it got accepted somewhere.
Did you reframe it as lessons learned from?
Yeah, I have both of them in there,
right.
But even the second experiment, I'm not sure if it's that much better.
Yeah. And I noticed this was 20 years ago. I mentioned I was trying to find information about why learning and a learning agent in in a training environment, why that wouldn't transfer to the operational environment, and I couldn't find anything because nobody would publish if their agent crashed and burned in the operational environment, figuratively. Nobody was publishing that. but they should, because that's an important set of parameters to learn. Okay, so the population is everybody. So if we talk about, hey, statistically speaking, at Embry-Riddle, students are at 40 credits, whatever the number is. Population would be all the students at Embry-Riddle. Now you have to bound that. What do you mean, all the students at Embry-Riddle? Okay, let's say all the students at the Daytona Beach campus. Undergrad or grad, you have to define everything. Okay, so let's say all the undergrads at Daytona Beach campus full-time. Now we can talk about, now we've defined the population. And if we wanted to find out what the average number of credits that population had, it's easy enough, in theory, to add them all up, divide by the number of students, and then you've got it, right? That is not statistics. What statistics is about is when it's not feasible to actually get the measurement from the entire population. So you try to presume or estimate the metric on the entire population by looking at a sample. Now, I said earlier, hey, that you're always asking the question in statistics, are these two populations the same? And that sounds, the way I framed that, that may sound like you're not asking that question, but you are. Because what you're doing is you're taking a sample of the population, you're performing whatever measurement that you are, whatever metric you are, and then you're claiming that that applies to the whole population. But what you're really doing is, again, you've made an assumption. You've assumed that the answer to the question of does the sample population and the entire population, are they the same? You're assuming the answer is yes. But as we've talked out, you can have we can have issues with that already, right? You can have selection bias, you can have sample bias, you can have even performance issues. If you built a simulator and it was a human in the loop simulator, so you've got a human interacting with the simulation. And just for the heck of it, let's say it's a flight simulator, because what the heck, we're at Embry-Riddle, right? It's a flight simulator. And then you run a bunch of humans through this flight simulator. You give them these scenarios, and we want to see if this course of action is better than that course of action. So you give them a scenario, and half of them run the scenario one way, half of them you do some kind of an intervention, an advisement, and they run the simulation, and then you want to see if the results are different. I don't know, maybe it's supposed to be I don't know what, I don't care what it is. Not important. Is there an issue with the fact that it's actually just a simulation? Could that cause a bias in your results? Absolutely. You put these people in a real airplane and you say, here's what I want you to do. I want you to fly under the bridge over the river. Right? And people in the real airplane might say, that sounds dangerous. I don't think I want to do that. As opposed to in the simulation, they're like, hell yeah, let's do it, right? Because in the simulation, there's no consequences. So what people have found in the military study this a lot, and they do military training simulations, is that people will take a lot more risk in the simulation than they will in the real world. And that's natural, because in the simulation, what the heck, you just get respawned and start again, right? Whereas in the real world, you have serious harm. So that alone can bias your results, yeah.
Modeling and sim have going for like three summers. And we saw that because we tested with the engineers and with real pilots, and the totally different behavior in sim versus the test pilots from there.
Yeah, and the trick there is even those test pilots know they could be way more risky. Who was more risky, the engineers or the pilots? Who was giving you the bad results?
The engineers.
Yeah,
because they would do really crazy things.
Yeah. So the way the military tries to pull that back is they do have something called doctrine. And in doctrine, it says, if this is the situation, this is what you should be doing. This is our doctrine. And they try to make sure that the people, whether they're training in airplanes or tanks or whatever, are maintaining doctrinally correct behavior. They still might take more risks than they would in the real world, maybe, but at least it's bounded by the doctrinal behavior. Yeah.
So we'll just follow the procedure.
The pilot, yeah.
So they still know how to fly it, but they will not. And they know the procedures too. They're taught.
Yeah, but they don't
But
care.
they won't.
Yeah, they don't care. I think pilots are, despite all the Top Gun movie type stuff, yeah, sure, they're brash and confident and all that stuff, but I think they also take a lot of pride in being doctrinally correct because they know that's how they stay alive too. Okay. So you've got the population, which is everybody. You've got the sample, which is a subset. There's always a big question about, as we've just discussed for a while, the deal with the sample. Is it large enough? Is it biased in some fashion? Because what we want to do is take the sample results and apply it to the population. Are those two populations the same? Is the sample population basically truly the same as the full population? And you can't do that unless you're convincing yourself that the sample is truly unbiased. Now, having said that, of course, you can still get an unlucky sample. That's why you try to do a large sample, so that the likelihood of getting the unlucky sample goes to nil. Then we have the idea of a distribution. Once you have provided your sample and you're performing some measurement, then you have distribution. What's the most typical distribution you hear about? The bell curve, which is the normal distribution. And it turns out in a natural phenomena, that bell curve tends to cover a lot of things. What's the average height of a human being? Okay, it tends to be a bell curve. There tends to be some median height, and then there tends to be symmetric variance on either side of that average height. Same with lifespan, weight versus age, things like that. They tend to be, in the world of natural phenomena, there's an average, and then we are symmetric about that average. Not all distributions are that way. So, and we'll talk about that in a little bit. Okay. The mean, which is just the average, is given by this definition of sum everybody up, divide by the number of samples, right? So you take whatever you're measuring, and obviously this is assuming a numerical value. What happens if it's not a numerical value? Then what?
You make it a numerical value.
You make it a numerical value. Have you heard of a Likert scale? You've done Likert scale, whether you've heard of the name or not. When they ask you at the end of the semester for the course evaluations, and they're like, the learning outcomes were clearly stated, and you either agree or disagree with the statement from 1 to and they're giving you not at all to very much, and they score that as 0, 1, 2, 3, 4. Which, by the way, at the end of that, they added a couple questions a few years ago, and for some reason, they score those questions instead of 0, 1, 2, 3, 4, they score them 1, 2, 3, 4, 5. And nobody could figure out in the faculty, why would you change the basis for your scoring? Because now we can't compare, right? Anyway, it's completely artificial. You simply put in, okay, not very much is going to be a 0 and blah, blah, blah. At the end, when you guys graduate or have graduated, did you do the graduating survey when you graduated? Yes, no, you should see if it's too late. So we look at those results and they ask a bunch of questions, and some of them are basically the ABET outcomes. And then we assign values of 1 to 5, and our criteria is we have to get a 3 or average out 3 or more. Which, by the way, that's not a very ambitious goal, right? What we're saying is the average student was like, yeah, I learned some stuff, you know. So the idea is that that's numerical, and if you have non-numerical data, you just have to artificially transfer, and then that can be another source of bias or issues. And people should argue with you as to the way you're setting up your statistics, because that's how you get a good model, right? You get a good model by having people throw darts at it, and you have to figure out, okay, you know what? You're saying I'm doing this wrong, but here's why I'm doing it. Here's why I think it's valid. Right? And if they find something that you really can't defend, that's even better news, because maybe it means that you can improve your model. Okay. So that's not a surprising, I'm going to make this a little bit bigger. That is not a surprising formula to anybody here. But here's where things start to get a little wonky. I think everybody is so comfortable with average, right? It's such an intuitive feeling. But now variation is something that is not as obvious. And so what variation is about is, once you know what your average is, then you're taking xi minus mu. That's a mu, right? Mm-hmm. Not a nu. It's a mu. It's a mu. Okay. X sub I minus mu. Okay, so what you're doing is you have the average, which is mu, and you're taking each individual value and you're subtracting it from, it's just subtracting the average from it. And what are you doing? You're basically saying, look, I've got a bunch of points, some are above the average, some are below the average, and the variance is going to be the sum of that, of all those differences. But here's the problem. Some of them are above, some of them are below, which means it's probably going to even out to 0, because that's why the average is the average. So it's very likely going to even out to 0 or very something close to 0. So whenever you have that situation where you've got some values that are above the line, some values are below the line, and if you add them all together, you're going to get yourself to 0. But what you really are interested in is how far from the average are they? But the pluses and minuses are screwing you up because they're interfering with each other. What's the standard thing to do? Take the absolute value. How do you take the absolute value? You basically square it and take the square root. Here, all they're doing is squaring it. We'll take the square root later on. You know, you've heard that term, root mean square? Oh, it's the square, right? It's the square of the delta from the mean and then the root of that. Oh, okay. So here we're just taking the square. And the reason that square is there is so that every distance from the mean is a positive number. That's the only reason they do it. Then you subtract by not n, but n minus 1. Now, why is it n minus 1? I used to know this. Why is that?
I used to know this too.
It has something to do with the mean, yeah. So I'm not going to. Okay, hold on. I'm sorry, I have to take a break for about 5 minutes. I've got some people doing construction on my house. So I'm going to pause this for a second. Let's do this. Okay. All right, so that's what the variation is. Now, what is that?
Oh, I figured out.
Oh, good. What is it?
It's to get an unbiased estimate of the population variance or standard deviation. It's called the Bessel correction. It's because you're estimating both the sample mean and the variance from the same set of data. So to take away the one so that you're getting biased.
I'm not intuitively seeing it still. I have to get it. Yeah.
But that was also just typical search.
Okay, yeah. Well, all right. I'll try to,
An AI overview one website.
oh,
So
I'm so mad at that.
I don't
AI. So it doesn't help. Yeah. All right. I'm gonna also think about that tonight and see if I can get I like to have um intuitive explanations, right? Like, here's what it really means. So the Bessel correction you're saying, and it's supposed to be accounting for so that you're not double counting something, it sounds like. So I
Yeah.
want to make sure that I want to figure that out. Now, by the way, with large N, it's going to have virtually no effect, right? Okay, but that is the variation. Now, the way to think of variation, when you think of variation, what do you think of? What is it really telling you? Just in everyday language.
Something is different from what you might expect.
Okay, right? So in terms of the bell curve, we said there's a median and then the bell curve is symmetric on either side. This is telling you how fat that curve is. That's what it's telling you. Is everything like way spread out? If it's way spread out, the mean doesn't have that much value to you because you can have values that are so wildly off the mean, right? To the left or the right. But if you've got a nice tight little bell curve, then what that means is everything is clustered around the mean. There's not much variance. And again, I said in natural phenomena, you tend to get that bell curve. And that's why when teachers are grading on the bell curve, and I don't think this happens much at all anymore. When I was a lad, this used to be a way college teachers would always grade things, is they would say, okay, we're going to take the students' test scores, and then we're going to fit it to the bell curve. And the average students should get a C. So the 75, the score of 75 out of 100 is going to be the mean, and then we're going to distribute all the students. And even if you got a 92 on the test, if everybody else was getting a 95, that means you got a D, right? So, I mean, it was really coercing the data to fit their mental model of how things should be. When teachers, it's more likely that the scores will be low, and then teachers will help you out by grading on a curve, right? And then what they're doing, it's the same trick. They're forcing the data to fit a bell curve distribution, and rather than giving you the raw score of what you got, they're going to give you some kind of a score based on the distribution. All right, so basically that's what that's telling you, is how fat things are. Then we get the deviation, and that's the square root. So when we talk about variation, that's just the deltas, every individual's delta from the mean squared to get rid of the negative values, divided by effectively the number of individuals, right? Number minus 1. And then in order to get deviation, you take the square root of that. And why are you taking the square root? Because if you kept everything squared, the numbers would be too big. So you take the square root. Now we're truly able to get a sense, when we talk about deviation, of how widely scattered the data is. And from there, we can talk about a standard deviation. And we can talk about the deviation is sigma. So we can talk about a 1 sigma event, 1 standard of deviation, or a 2 sigma event, 2 standards of deviation, or a 3 sigma event. And so you may occasionally hear that term out in the wild. 1 sigma, get my numbers right. 1 sigma is 64% roughly of the total population. 64, 65, 64 and change, isn't it? Something like that. And then 2 sigmas is, it's not, I think you have to get up to 3 sigma to get 95%. Right. But basically each sigma is telling you, each standard deviation is telling you what percentage of the population is fitting under that umbrella. And it's also telling you what isn't. So if you have, if you hear people say, oh, that's a 4 sigma event, meaning I think it's like only 1% of the population is outside of that range. And what they're saying is that that event that occurred was so rare, it only happens, 1% of the time. Of all the possible events that occur, 1% of the time. So if a river floods every 10 years on average, and then it floods 10 feet high on average, but then you get a 30-foot flood, then you might say, oh, that was a 4 sigma event. Meaning, of all the times it ever floods, it only floods that high 1% of the time. It floods every 10 years, and therefore only 1% of the time it floods that high, which means basically every 1,000 years that you might get a 30-foot flood. And you're hearing that kind of phrasing a lot recently with the extreme weather that we're having. Oh, this is a 1,000-year event. Well, we've had 3,000-year events in the last 3 years. So that's what, when people say that, I mean, you hear it on the news. That's what a meteorologist might say, or a climatologist might say. Oh, this particular event is a 1,000-year event. That's what they're telling you. Okay. Monte Carlo simulation. Now that we have those basic things. Monte Carlo simulation is one that relies heavily on randomness. And so, again, people shy away from random number generation, I think, because they think it might be childish or not sophisticated. It can be very helpful, very helpful. There's a problem called the max flow problem. And the max flow problem says, basically, I've got a bunch of nodes connected by edges, and the edges are pipes, and each pipe has a certain carrying capacity. So it can carry a certain amount of fluid through. And what I want to know is how much fluid can flow through the whole network, the maximum flow. This is called the maximum flow problem. How much can I flow through the network? One way to solve that problem is to take a unit measurement of fluid and flow it from one end to the other. And if it works, great. And if it doesn't, you back it up and you try another path. And you keep doing that one at a time, adding 1 unit of fluid to the system at a time until finally the entire system is saturated. And now you know what the maximum flow is. The problem is that's a computationally expensive thing to do. It's an order n cubed problem for those of you that understand computational complexity. Another way to solve the problem is to just try randomly assigning weights, assigning values of flow to each of the pipes randomly, Monte Carlo. And it turns out that you can get, just by random guessing, you can get to like a 95% solution fairly quickly through pure randomness. Now, what happens is you go from an order n cubed problem to an order n squared problem. So you save a lot of computational cost. And the fact that you didn't get a perfect solution, you got a 95% solution, people are willing to pay that cost for it. But that's a notion of a Monte Carlo simulation. It's just random. You want to do in your motorcycles, how is their behavior going to be generated? Right? There's going to be some randomness there. It's not purely random behavior, but hey, should I shoot the gap between these two cars? Sometimes the answer is yes. Sometimes the answer is no. It's an agent, right? So it's a decision maker, but it can be a decision maker who basically is going to roll a dice and say, yeah, sure, I'll do it. And you can bias that, right? If the gap is wide, if the gap is narrow, it may affect their decision. But it's still ultimately going to come down to a random number generation. And so in agent-based simulations, because agents are deciders and we don't want the outcome to be deterministic, having some degree of randomness inside your simulation makes perfect sense. Now, within yours, you don't have to have any randomness, right? You can establish rules and the system follows rules. But then you can play the game of what happens if I allow, instead of a single deterministic rule, I pass this value along, I pass a value plus or minus, and we'll call it noise or something like that, plus or minus some kind of a variance. And then you can explore things like how much variance can the system handle and still come to the same result. Those kinds of questions start to become interesting. But that would start to bring in this degree of you don't want to hard code your variance, because now you've got a deterministic system again, and that's no fun, right? We like it when the systems are non-deterministic. The fact that they're non-deterministic, Joe, jumps us immediately into a statistical world, because now we have to take a number of results, right? And then say, okay, here's the mean, here's the deviation, blah, blah, blah. You may find that your data does not follow a normal distribution. Is that a problem? Not really. No, people will still accept it. Yeah. There are other distributions. And all of these, this notion of deviation, these formulas are built for the normal distribution, the bell curve. We have others. I'll talk about them in just a second. I have not explicitly looked for, but I have a firm belief that they exist. That the notion of deviation can also be created for these other forms of distributions. And I don't know if there would be a distinction in how they would be calculated. Now, ultimately, we're going to get to remember the Z table from, you guys have all taken MA 412 or something like it, right? Remember the Z table? Remember how to use the Z table? I never remember how to use the Z table. Yeah. So, I found a great website, by the way. I'll post it. So I always have to look it up again. Yeah, because I do this only once in a while. So what's the Z table asking? The Z table is saying, okay, here's two sets of data. They've got slightly different means. Are these means far enough apart that it's statistically significant, right? That's what the Z table is trying to answer that question. So the values that show up for the Z table are built for the normal distribution. I don't know if they would be different for different kinds of distributions. But there are different distributions. How many of you guys have used a random number generator in a programming language like Java or MATLAB or something like that? You've all done it, right? Generally, modern programming languages have a function called random. And the random function, as a rule, returns what? You call the function, what do you get back for most programming languages? What's your expectation?
A random value between 0.
A random value between 0 and 1. Is it normal? Do you normally get half and then there's a distribution on the side? No. You're just as likely to get 0.1 as 0.5 as 0.9, right? There's a word for that. What's that distribution? That's a flat, we call that a flat distribution, right? So instead of the bell curve, it's flat. Every point along the scale is equally likely. When is that useful? By the way, when you do your Monte Carlo simulations, you're going to probably use a flat distribution. You can, I think many programming languages will support a random number generator with a normal distribution, but you have to ask for it specifically. And if not, you have to build it from scratch. So anyway, when would you use this? Any situations where you might use this?
Whenever you want.
Yeah, as a general rule, again, as a general rule, when you're going to do a single event, you tend to want to have a flat distribution because you want all outcomes to be equally likely. Generally, if you have outcomes that are more likely than others, then you weight them somehow. And then that single event will be filtered through a weighting system to tell you what the actual outcome is. You can do that pretty easily. Like, okay, I'm going to do random number generator, and if it's between 0 and 0.75, we're going to take action A. And if it's between 0.75 and 0.85, we're going to take action B. Well, what have you done? You've taken that flat distribution and you've weighted it, right? By giving a larger range of values to action A than action B. Flat distributions tend to work for single events. The bell curve, by definition, how did we start talking about it? Right away, we were talking about multiple events, right? Here's the average, here's the variance. Multiple events. Flat distribution, a single event. If you do a single event over and over and over again, should you get a bell curve? Should be able to, right? That should happen. Okay. Let's talk about different distributions briefly, then we'll go into. All right, so even distribution or flat distribution, everything is likely to occur. Geometric distribution, this one measures the number of events likely to occur before the first failure or before the first event, an event of interest. If you are planning on maintaining a physical system, and that system, let's say, you've got five production units, each one of them has a motor in it. When should you expect to have to cough up the cost to replace one of those motors? It's this distribution. You tend to use them for that, before the first failure. Have you heard of the term mean time before failure? That's what they're talking about. People have to worry about this. When the submarine goes out for 6 months, it's going to be underwater for 6 months at a time, how many light bulbs should they bring on board? How many air scrubbers? How many this and that, right? There's just an assumption that something will fail, and you have to have replacements for that. That's slightly different than this Poisson distribution, which is used for time between two events. So if you have, this is used in queuing models. The queuing model says a customer came in the door. How many minutes will it be before the next customer comes in the door? And so you have this notion of a different distribution. I should add the pictures of these distributions to this slide, shouldn't I? That'd be nice. So they're used for slightly different things. The normal distribution is the one we normally talk about, right? It's the one that it's the most common. It's the one that occurs in nature in terms of getting a collection of events and determining what the average and the variance is, and the variance is symmetric about symmetrical at the mean. The geometric and the Poisson distribution, these are like one-sided events, right? They don't have a mean with a left and a right. They have a 0 and out, right? What's for geometric distribution, the say time between failure, but before first failure? Well, time starts at 0, right? Time now. Does this thing fail a minute from now, a month from now, a year from now? That kind of thing. There are things called infant death. Have you in terms of mechanical things? Have you heard of this term? You build engines, and then before they go out the door, you test them and make sure that they run. And you may have how do I want to say this? You have a distribution of them that over time will fail, and it's a fairly low number. 1 week out, 2 weeks out, 1 year out, right? And then once you get to this where you're likely to get to the first failure, then it starts to go up, right? The number of failures will go up 10 years out, whatever. But right at the factory, there's this little blip of failures. and it's engines that were just built improperly or something happened weird during the manufacturing process, and they fail before they even go out the door, or they fail within a very short period of time. That's called infant death, but it's referring to mechanical systems, not obviously real live babies. Okay, so be aware that these things are out there. You're going to deal with normal flat or even distribution for single events. You're going to deal with normal distribution for trying to normal distribution for trying to collate a bunch of single events and get a statistically meaningful result. If you are doing time between two events, you may want to look at not having the time between two events fall on a normal distribution, because again, you're only looking at one event at a time. You may want to use some other distribution to develop that one event. And again, after you do that one event many times, you can collect those results and get back to your normal distribution. But that one event inside your simulation might be, again, the arrive. Like, how often do motorcycles arrive in the traffic pattern? Right? This might be a good way to go. Instead of just saying every minute plus or minus 10 seconds, which is normal because it's symmetric, you might say at least a minute and increasingly likely as you go out in time, kind of thing. Okay, that's what I have for today. Tomorrow we'll go through examples and play with the Z-table. For the rest of the day, let's talk. Let me turn all this stuff off, and then we'll talk about your reports.